One of the biggest mysteries on the flat Earth is the sunset. How can a sun that is always 3,000 miles above us seem to set behind the horizon on a flat Earth? There are many ways to explain this, but let's look at a sunset first. This is a sunset at the North Sea beach, and you see how the sun slowly sinks behind the horizon until it's completely gone. How is this possible on a flat Earth where the sun is always 3,000 miles above us? Let's look at this map of the flat Earth, with the green circle is the pole circle for the North Pole. The yellow circle is the Tropic of Cancer, the most Nordic place where you can see the sun right above you. Then there is the red circle, the equator, dividing the Earth in the north and the south part. And the last is the Tropic of Capricorn, where the sun is right above you once a year, and it's the most south part where the sun can do that, and the pole circle for the South Pole. Now let's introduce the sun. Today the sun is right above the equator. The little yellow ball is the sun, and the large yellow translucent circle is the circle of light the sun casts on the Earth. The edge of this circle is the place where sunset and sunrise takes place. When you look at the Earth, there are 24 white lines on it. These are the hour lines. There are 24 hours in the day, so there are 24 of these lines. And now we start to move the sun like it does in a day. The sun moves over the equator at this moment, and it shows you how day and night works on the flat Earth. But there's one thing, it doesn't explain why the sun is setting, and we'll try to use the most common reason why the sun should set on the flat Earth. It's called perspective. Look at this train, you see how it disappears in the distance, it rides to the horizon, and it disappears when it gets smaller and smaller. But there's one thing, the train will never sink behind the horizon. How will the sunset look when you have perspective to make it work? You see the sun is slowly going down, like the train was going up to the horizon. The sun is going down to the horizon and is getting smaller and smaller. The sun with perspective can never, I say never, go behind the horizon. It will always stay above it, but at a certain point we will not see it anymore. You can see it now, it's disappearing. Why does it not work like we observed in the first video? Well, we have to do some math to explain it. At first we need to know the distance from the observer of the sunset to the sun. So we need to know how far the sun is away from the observer during sunset. So we know the equator has a length of 24,900 miles. We put that number in our calculator. And now we know we can calculate the length of the arrow, so the length of the distance of the observer to the sun. It's about 4,000 miles, but that is calculated from the North Pole, and our observer is not at the North Pole but a little bit further away. So we add 1,000 miles for that. And so we can say that the observer is about 5,000 miles away from the equator. But the sun is not lying on the equator, but it is hovering 3,000 miles above the equator. So we have to calculate that number too. It's 3,000 miles, is what people say. And now we can calculate the real distance from the observer to the setting sun. It's done with the theorem of Pythagoras, who said that a square plus b square is c square, and c square is the line to the setting sun. Now, so a is 5,000 miles, so let's put that in our calculator. Of course, first clear it, then put 5,000 in our calculator, square, and then add 3,000 in our calculator, square, that's 40, that's that. And now we take the square root, and it's about 6,000 miles away from us, the sun. That is roughly the distance from the observer of the sunset to the sun. 6,000 miles. That's 2 times the distance a person on the equator has to the sun when the sun is at noon right above them. So it's 2 times that distance. What does that mean for perspective? Let's look at this train track. You can see this pole. The height of this pole is very clearly visible. The second pole is twice as much away, and you see that the height of that pole is more than half of the height of the first pole. And the third pole is a little less than half the height of the first pole. So a pole that's 3 times farther away is just a little bit smaller than half the first pole. And that's not what we see with the sun. And we see the sun set behind the horizon. Many people say, yes, but when you zoom in on that sun, when it is a little bit behind the horizon, you will see that it is above the horizon. So I did that. I took a zoom lens and took the first picture, and now the second picture with a zoom lens 2 times as long. We still see the sun setting with the same amount of the sun behind the horizon. So this is not perspective. Let's see another picture. Again, a picture I took with the smaller telelens, 210 millimeter, and this is what we see from the sun. A small part of the sun disk is still above the horizon. When I take the larger zoom lens, 400 millimeter, we see a sun, here it is, a bit at the same height above the horizon as in the first picture. So we see that the sun is really going behind the horizon. So we have to find another explanation for the sunset on the flat earth. It can't be perspective. And here is the real answer to the question, how does the sunset works on a flat earth? And the answer is, it doesn't work. It only works as we observe it when we are standing on a globular spinning world. So people, we have to accept Galileo was right, the church was wrong.